Section 7.1 is on exploring exponential models. The general form of an exponential function is as follows. Y equals a times b to the x, where a is not equal to 0, b is greater than 0, and b is not equal to 1. Notice in this equation that only the base b is being raised to the power of x. So if you're evaluating this, you're going to do b raised to the power of x and then multiply it by a. The base b is a constant. The coefficient a is the y-intercept. The exponent x, that's your independent variable. Its domain is the set of all real numbers, and its range is y is greater than 0, and the asymptote is the line y equals 0. An asymptote is a line that a curve approaches but never touches, and you'll see that when we go to graph some of these. Now, if a is greater than 0 and b is greater than 1, then the function represents exponential growth. As the value of x increases, the value of y increases exponentially, which means really fast, following an exponential curve. If a is greater than 0 and b is between 0 and 1, so in other words a fraction between 0 and 1, the function represents exponential decay. That means that as the value of x increases, the value of y decreases exponentially. So here's an example of a couple of basic functions here. So here we have the graph of y equals 2 to the power of x, and this is what we would call exponential growth because my base b is greater than 1. Okay, and notice that I put in values for x and figure out what y is. Recall that, in fact, let me just do this first one right here. So if I were to do 2 to the negative third power, that's going to be 1 over 2 to the positive third, or 1/8. So that's how I got all of those fractions. Okay, and this is a little bit of a different function because we're used to having x as our base and then we would raise it to a number power. Here we have a number as our base and we're raising it to a variable power. So it's going to give you a curve that looks like this. Okay, here's an example of exponential decay, and that would be 1/2, a number between 0 and 1, raised to the power of x. Okay, and so this would be, let's just take a look at this. So what would 1/2 to the negative 3 power be? Okay, that would be 2 over 1. So flip it and make the exponent positive, or that's going to give me 8. Okay, so as you can see, that's kind of flipped. Actually, it is flipped over the y-axis for our first function here, and this represents exponential decay. As x gets bigger, y gets smaller really fast. For exponential growth in the equation y equals ab to the x, with b greater than 1, the value b is called the growth factor. If something is growing exponentially, it increases by a constant percentage each time period. This percent increase, r, is called the rate of increase or the growth rate, and b is equal to 1 plus r, the growth rate. For exponential decay in the same equation, where b is between 0 and 1, the value b is called the decay factor. If something is decreasing or decaying exponentially, it decreases by a constant percentage each time period. The percent increase r is called the rate of decay and is usually expressed as a negative number, and as above, the base is equal to 1 plus r. Here's a little box from your textbook that gives us an equation for exponential growth and decay. So the amount after t number of time periods, so a of t, is equal to the initial amount times 1 plus the growth rate or decay rate raised to the power of t, which is the number of time periods. Let's take a look at an example of this. You buy a savings bond for $25 that pays a yearly interest rate of 4.2%. What will the savings bond be worth after 15 years? So we're going to use this equation. A of t is equal to the initial amount times 1 plus r raised to the power of t. Let's identify what our variables stand for. A is the initial amount, so A is $25. My interest rate is 4.2%. I need to write that as a decimal. And my time period, I'm investing this, or I'll hold on to the savings bond for 15 years. So So let's plug those values in and evaluate that. So the amount after my time period of 15 years is going to be 25 times 1 plus my rate raised to the power of 15. So let's go ahead and simplify inside the parentheses. That's going to be 1.042 to the 15th power. Now when we go to evaluate this, do not multiply these two numbers, okay? Order of operations tells us that we need to evaluate exponents first. So I'm going to raise 1.042 to the 15th power and then multiply it by 25. When I do that in my calculator, I get 46.3399 and a whole bunch more digits, okay? And since this is money, I'm going to round that to 2 decimal places, so $46.34. So that $25 savings bond that pays an interest rate of 4.2% is worth $46.34 after 15 years. Let's take a look at another example here. And this says you open a savings account that pays 4.5% annual interest. If your initial investment is $300 and you make no additional deposits or withdrawals, how many years will it take for the account to grow to at least $500? So we'll be using the same formula. A of t is equal to the initial amount times 1 plus the interest rate raised to the t. Let's identify our variables. The amount I deposit is $300. My rate is 0.045. What I don't know is the time. That's what it's asking me for, and how many years. And then will my eventual amount be at least $500? So that's my big A. So let's plug those in. So 500 equals 300 times 1 plus 0.045 raised to the power of t. So let's simplify that a little bit. 500 equals 300 times 1.045 to the t. Now this is going to be a little hard to solve, but I can clean it up a little bit. If I divide both sides by 300, this turns into 5/3. And here I have 1.045 to the t. Now I really don't know how to solve for something that has my variable in the exponent. So I'm going to go into my calculator. And I'm not going to show you here, but in the calculator, you're going to put into y1 1.045 to the x, okay? And instead of looking at the graph of this, I'm going to go into my table, and I'm going to try values of x. So choose x values, okay, until y is approximately equal to 5/3, which is approximately 1.67. Okay, so you're going to choose some x values and wait until you see a y value that's close to about 1.67. I did that and I got that t was approximately equal to 12, or in this case it's going to be 12 years. Okay. If the growth or decay factor of b is not given, if I don't know what that factor is, but you do know two y values for two consecutive x values, you can find the rate of change, which is r, using r equals y2 minus y1 over y1, and then find b using 1 plus r. Let's take a look at an example of that. The initial value of a car is $30,000. After 1 year, the value of the car is $20,000. Estimate the value of the car in 5 years. So my R is going to be Y2, which is 20,000, minus Y1, which is 30,000, over Y1, which is 30,000. And that's going to give me a negative 1/3. So that's my rate. So I'm going to use my same formula. A of t is equal to my initial amount times 1 plus r raised to the t. And I need to know the value of the car in 5 years. So my t is 5. My initial amount was the initial value of the car, which was $30,000, times 1 plus a negative 1/3, or 1 minus 1/3 to the 5th power, or 30,000 times negative 2/3, I'm sorry, positive 2/3 to the 5th power. And then I'm going to grab my calculator and I'm going to do 2 divided by 3, enter, raised to the 5th power, enter, times 30,000, and I get $3,950.62. So in this section, we learned a little bit about what an exponential function looks like and how we can use an exponential function to model a couple real-life examples, that is annually compounded interest and depreciation.